That's what I thought. Let's move into chapter 4.
Did you grade him already? It sounds like you did.
After a few years of teaching, you can sort of sense what is or is not happening in the room during an exam. All right, let's get into chapter 4. Transients. Oh, and these, never mind, I won't go there. These are electrical transients. Okay? Hopefully this will not be you in a few years. After you've attempted 207 5 times, you've now become a transient. Sorry. So we're going to avoid that. Here is V sub S. Here's R. Here's C. And now we have a different circuit. On the exam, you just had R's and sources, voltage and current. Now we have resistors and capacitors. But what do we know about this current that's flowing through that circuit? What about R and C? Are they in parallel? They're in series, aren't they? The same current is flowing through those circuit elements. That hasn't changed. KVL still holds. Eli and ice, we need to use now, especially if V sub S is time varying. But what do we know about the capacitor? And this you can always keep in your head. What do we know about I on that capacitor? And this I sub C is the current through the, it's an induced current, isn't it? It's not really going, but if the current is time varying, it looks like current is flowing through that capacitor because of this getting pushed. Remember that dance that never mind. That's why you will not see me on whatever that show is. Dancing with the Stars? Yeah. Won't happen. But you guys don't watch TV anyway because you're studying for 207 exams, right? Right. You will be now. I sub C. What do we know about I sub C? We know ice, don't we? We like ice. We're in the desert. Ice is equal to C dV sub C dt. And what we're going to do is we're going to use that to our advantage. And this voltage is our critical variable. That's where a lot of information is sort of stored or contained. That's telling us the state of this capacitor. That's what you might hear called a state variable. And because of that, we are going to write the equations that govern the dynamics of this circuit, or we're going to write the equations of motion. When we have capacitors, we're going to use those capacitor voltages to write those equations. We're going to write equations of motion in terms of V sub C of t. And for these first order transients, or maybe let me just go back. What do you know about the energy storage elements in this circuit? Which of these elements can store energy? The capacitor. And there's only one capacitor or a capacitor equivalent. You could have had two capacitors in parallel, two capacitors in series, and now you've combined them. You effectively have one capacitor. With that one energy storage device, you're now looking at a first-order differential equation. If you had a circuit that contained four capacitors interconnected, you would be looking at a fourth-order system. For Chapter 4, we're only dealing with one, or an equivalent. So we only have first-order differential equations in the first part of Chapter 4. We will actually start putting resistors or inductors and capacitors in a circuit. There's two energy storage devices. Now we have a second-order differential equation. Question?
So the voltage source, someone once told me like a battery could be a voltage source. Is that a way of storing energy?
Well, the question was, is that voltage source a battery, and doesn't a battery store energy? And yes, it does. And what I'm meaning when I say how many energy storage devices do I have, I'm meaning of the other elements besides the sources. So right now, that V sub S might be a power supply or voltage supply in the lab. And we're not worried about whether that can or cannot store anything. We're worried about what we've connected to it. And that circuit that we have connected to that voltage source is what we're now saying, what of that remaining circuit can store energy? So your question is valid. If you had a battery, yes, that can store energy, but typically these batteries are constant, and now we're into a DC circuit, which isn't going to be too exciting except for the initial transient, and that's what we're going to try to learn how to analyze. We have one energy storage device of the passive elements in that circuit. It's the capacitor, and now that we have a capacitor, we want to write these equations that govern the dynamic behavior of that circuit in terms of the capacitor voltage. If you wanted to write a circuit equation, and you said, oh, I see that. If that capacitor was a resistor, what kind of an equation would you be thinking you wanted to do? What makes you feel warm and fuzzy? KVL, right? That looks like it's begging you to write a KVL equation. Well, that's true for this one. When we have this series connection, it's begging us to want to write a KVL. So let's just do that. If we started in the lower left-hand corner, we would have minus our source because we're going in the negative terminal. These KVL equations are going to be the same, thankfully. We're not changing those. Plus the voltage dropped across the resistor, which is R times I. You could have said V sub R, and then we could go the next step and say R times I. I'm going to avoid that. Maybe I shouldn't, because now I'm going to not. I'm going to say plus V sub C of T. But we said we want to write these equations in terms of the capacitor voltage. V sub S we're going to assume is given or known. What we want to do then is solve this for the unknown. But right now, darn it, I have I and V. I have two variables in there that I do not know. It would be nice if I could eliminate or get rid of one of those and just have one equation and the one unknown. And what do you think I'm going to use to get rid of one of those variables? You're going to use ice, aren't you? So it's like you hit your head and you have a sore head, you're now going to use ice. You're going to use that right there, correct? Because you want to write this equation in terms of your capacitor voltage. Ice is your friend, remember? We get rid of I by C dV dt, and we now end up with then minus V sub s of t, plus r times ice, which is c, dv sub c dt, plus v sub c of t is equal to 0. Or you could say, oh, that's just rc dv sub c dt plus v sub c of t is equal to v sub s of t. And that should just make you feel really comfortable. What is that? A first-order differential equation, which is what we were expecting because we had how many energy storage devices? 1. We should expect a first-order differential equation. Or you might see me write that as v sub c prime of t, where the prime means derivative with respect to time. And now all I've done is divide both sides by RC, so that I now have, and I've solved for the highest powered derivative on the left-hand side. Doing that, I now move the v sub c to the right. That gives me a minus, but I've now divided everything by RC. And that's an equivalent first-order differential equation, describing exactly the same set of dynamics. Questions on that? That's our first-order transient due to a capacitor, and that's actually a filter. You now, if you had a signal in that supply, V sub s, maybe that was actually coming to you from a transducer, and it had noise on it. That signal had noise. You could actually pass it through this RC circuit and measure the voltage across that capacitor, and it's going to actually low-pass filter that noisy signal. If you low-pass filter a noisy signal, what are you doing to that noisy signal? Or where is noise in frequency? Give me some ice, my head hurts. Give you a capacitor, right? What? It's really not that funny, is it? I'm sorry. What time is it? Time to leave. I can kind of hear you. I'm trying to make it so it's not quite so painful. Maybe you'll bring ice next time, right? When your head starts hurting. Where were we going? Oh, not home, not yet. We had a noisy signal, and noise is usually high frequency. And a low-pass filter is trying to get rid of or reduce that noise, that high-frequency content. We've now designed a low-pass filter. Did you know that? Maybe not, but now you do. Oh, and I still want to lift up this floor. After class, sorry. This is now, this, if we attached our instrument that we're measuring to this particular set of terminals, that's just the capacitor voltage. But if this was some transducer voltage and it had a bunch of noise on it, by that I'm meaning the following. If that V sub s looked like should label it with what I said it was. If it looked like that, now maybe after we filtered it with this RC low-pass filter, maybe it now looks more like this. And this is now V sub c of t. So as a design exercise, you might be asked to design that low-pass filter. And RC is actually the time constant of that low-pass filter. I'm getting a little bit ahead of ourselves, but I wanted to motivate you to think, well, he's just giving us stuff to give us stuff. No, I'm giving you stuff so that you understand some of these terms and concepts. Here's a a noisy waveform V sub s of t, which maybe isn't coming from a battery, but it's coming from a transducer. You've now filtered it, and maybe that's more what you want to say is driving something else that you might want in your system, is that smoother curve. And that's a low-pass filtered version. Very ideal in terms of the sketch, but hopefully it presents the concept or the idea. And that wasn't too difficult to design, was it, in terms or build? A low-pass filter is just an RC circuit. It's first order. If you wanted to do a little bit more or be better, more effective at getting rid of that noise, you might want a higher order filter, which is maybe why you want to put some more capacitors in there. We're not going there yet. We're still in the first half of chapter 4. Let's look at the same thing, or a similar thing, for an inductor. What do we know about an inductor in terms of its current voltage relationship? It's Eli, isn't it? So Eli is our friend, but we probably won't be sticking him on our forehead, will we? Like ice. Sorry. Here's V sub L of t, and they're leaving in droves after that. Gosh. V sub L is L di dt. There's Eli. What kind of a circuit can we draw now? Let's draw the following. Let's say that we have a current source, an inductor, and a resistor. Here's R, here's L, here's I sub S. How many energy storage elements of the R and the L are there? 1. What kind of an equation do you think makes you feel warm and fuzzy? KCL. We have one node, we have this voltage, V, but now since inductors and capacitors are these dual entities, here's, let's say, I sub L, here's I sub R. KCL tells us that we have I sub S is equal to I sub L plus I sub R. Eli is V is equal to L di sub L dt. What do you think variable-wise are we going to write equations in terms of for inductors? If an inductor is a dual element to a capacitor. We isolated on this piece before, which was the derivative term in our capacitor. That was capacitor voltage. Now we want to write our inductor relationships in terms of inductor currents. Meaning when we're writing these equations, we want to write the equations of motion, or the dynamic equations, in terms of I sub L of t, which is our inductor current. Doing that, we now want to rewrite that KCL equation. We want to put in place of I sub L and I sub R expressions only containing I sub L's. Well, I sub L is I sub L. I'm going to leave that one alone. Meaning I now have I sub S of T is equal to I sub L of T. Well, now how in the world am I going to write I sub R in terms of I sub L? Ohm's law tells me that, correct? V over R, V sub R over R. But what do we know about this resistor's voltage in this particular circuit? It's exactly the same as the inductor voltage. And we know by Eli what that inductor voltage looks like relative to the current through that inductor. Meaning we can now rewrite this V sub R. You know what, I just kind of want to play color. I'm reverting back many, many years and coloring in the afternoon. V sub R is L di dt, meaning we now have L di sub L dt all over R. And that's actually what I need, right? That's a first order differential equation. But I can clean that up a little bit because maybe it doesn't look very neat. But I can say that's L over R di sub L dt plus I sub L of t equal I sub S of t. Or how else could I write that? So this maybe looks better, but hopefully it's clear that that's exactly what I just had before. I can clean that up by solving for the highest power derivative. That's a first order differential equation, isn't it? Which is what we expected. We had one energy storage device. If I multiply all the terms or both sides through by R over L, I'm going to get rid of that coefficient, or I'm going to normalize the coefficient on that highest derivative. I'm going to make it monic. It's going to become 1. Throwing some terms around here. Oh, and I didn't do it that way before, did I? I replaced my derivative with something that's quicker to write, which is I sub L prime. And that's now going to equal what's left. That's minus R over L I sub L plus R over L I sub S. Again, a first order differential equation. Questions on that? Why are we packing up? Oh, that hurts. Questions? I'll go get some ice. I'll be okay. What's happening a week from today? No class, but you will have material that you will need to watch. I'll see you on Tuesday. Have a good weekend.